The current frenzy around AI focuses almost entirely on the brains, the massive amounts of raw processing power required to train the world's smartest models. These Nvidia GPUs are the highly prized engines of the revolution. As the Nematron Coalition demonstrates, massive industry groups are forming to secure this hardware. Yet, even with multi-million-dollar data centers, these processors are hitting a physical wall. The fastest chips ever designed are struggling to stay fed. This is processor starvation. It's the equivalent of $1 million hypercar forced to crawl because its fuel line is the size of a drinking straw. The engine is capable of incredible speeds, but it can't get gas fast enough to function. We have reached a point where processing speed has outstripped data delivery. The ceiling of the AI race is now defined by the physical logistics of computer memory. Standard computers use a flat 2D layout, where memory sits inches away from the processor. Traditional software requests data slowly, but AI demands millions of parameters instantly. Trying to jam this AI workload through a narrow 64-bit highway creates a massive physical traffic jam. This bottleneck has a direct financial cost. These processors often sit idle, wasting expensive electricity while they wait for the physical roads of the motherboard to deliver the next block of data. High-bandwidth memory solves this through spatial engineering. Instead of laying chips flat, engineers stack them vertically into a 3D skyscraper. Then this memory tower is placed directly next to the processor on a shared base layer called an interposer. This reduces the physical distance the data has to travel to mere micrometers. Providing enough data to an AI chip required a total departure from standard computer architecture, shifting from 2D sprawl into this highly condensed 3D footprint. Vertical stacking creates a new problem. If you have 8 layers of memory pressed together, there is no easy way to extract data from the layers trapped in the middle. The solution is through silicon vias, or TSVs. Thousands of microscopic holes are drilled straight through the memory layers and filled with pure copper. This creates parallel pathways, establishing a direct connection from every floor down to the base. This architecture replaces the narrow 64-bit highway with a mega highway over 1,000 bits wide. A single stack can now move terabytes of data every second. HBM ends processor starvation by fundamentally changing the physics of the road. Opening thousands of parallel lanes allows data to move in colossal blocks rather than single files. While the performance of HBM is efficient, the physical reality of manufacturing it is incredibly punishing. Traditional 2D chip production, shown here on this silicon wafer, is a highly automated process. Because the layout is flat and simple, these factories enjoy yield rates, the percentage of working chips, of over 90%. HBM requires extreme precision. Manufacturers must align 12 microscopic layers, drill thousands of holes, and bond them together flawlessly. This leads to the known good die problem. If a single copper connection fails, or one layer has a microscopic defect, the entire 8-layer stack is unusable. You cannot disassemble the skyscraper to fix one floor. You have to throw the whole building away. This complexity drops success rates from 90% to between 60 and 70%, meaning 30% of this expensive material ends up as scrap. The requirement for absolute physical perfection has turned computer memory from a cheap, abundant component into a scarce and extraordinarily expensive bottleneck. Because HBM is so difficult to build, power has shifted to the tiny group of companies capable of producing it at scale. Facilities like this Micron complex represent one of the few places on Earth that can meet the demand. Tech giants are currently competing to lock down these supplies, often prepaying for years of inventory just to ensure their data centers stay operational. Companies like Samsung and SK Hynix now hold significant leverage over the entire AI industry. This scarcity has fundamentally changed the economics of the sector. Because these manufacturers are capturing much higher profit margins than they did with standard chips, Wall Street has begun to revalue memory suppliers as premium AI infrastructure plays. However, the memory industry has a history of cyclical trauma. In the past, high demand has led to overbuilding, followed by a sudden supply glut and a market crash. Investors are watching to see if AI demand can break that boom-and-bust cycle. Ultimately, the trajectory of AI depends on these vertical structures and the precision required to build them. While the software continues to evolve, The real breakthroughs are currently measured in the microns and copper connections of the silicon skyscraper.